Welcome to this video that explains the Malthusian trap. Consider a community where the amount of grain harvested depends on the number of peasants farming a shared agricultural piece of land. To be specific, consider a production function y, or a function of x is equal to 100 multiplied by x raised to the power half, where y is measured in bushels per year and x is measured in number of peasants. Assume that we have 0, 100, 200, and so on until 1000 peasants working the piece of land. Our next order of business is to calculate the community's total product. So in the table on the right, the first column represents X, or the number of peasants, while the second column represents Y, or the total bushels or total product. So to calculate the total product, we use the production function, which is Y is equal to 100 multiplied by X raised to the half. And starting with the first 0 number of workers, our total product will be 100 multiplied by x, in this particular case, which is 0 raised to the half, and that gives us 0. 0 is indicated in the table. For 100 peasants, we have 100 multiplied by 100 raised to the power half, which gives us 1000 as total product. For 200 peasants, we have 100 multiplied by 200 peasants raised to the power half, which gives us 1414 as total product. And finally, for 300 peasants, we have 100 multiplied by 300 raised to the power half, which gives us 1732 as our total product. So going on with the same process until 1000 peasants, we get those values. Having calculated this total product, we can illustrate this information in a graph where we have total product on the y-axis, or the total bushels on the y-axis, and number of peasants on the x-axis. So we're simply graphing total product against number of peasants, and we get a production function that looks like that. So you should take note that this production function is shaped the way it's shaped, in a concave form, because as we increase the number of peasants, the total product increases, but it increases at a decreasing rate. Having calculated the total product and illustrated the production function, it would make sense to also calculate the community's average product. So average product is defined as total product divided by the number of peasants. So for number of workers, average product is equal to 0 divided by 0, but we know that anything divided by 0 is undefined, so there's a blank in the first cell. For 100 peasants, it would be total product divided by number of peasants, which is 1000 divided by 100, and that gives us 10. For 200 peasants, we have average product given by 1414 divided by 200, which gives us 7.07. For 300 peasants, we have average product of 1732 divided by 300, which gives us 5.77. Going on with the process until the end, those would be average product values. Similarly, we can illustrate the average product on the graph. So let's assume we're looking at number of peasants of 200, and we had calculated the average product to be 7.07. Tracing the 200 on the graph from the number of peasants axis, we can connect a ray from the origin to the production function, and the slope of that ray would give the average product of 7.07. Similarly, if we picked 1000 number of peasants, we would draw a similar ray from the origin, and the slope of that ray would give average product of 3.16. An interesting question that one would ask is, what is the relationship between the average product and the number of peasants? So graphing the average product against number of peasants, we would have a negative relationship, and that negative relationship is coming from the fact that as the number of peasants increase, we notice that the average product was reducing until the value of 1000 number of peasants. So when we graph those values that we found before, we would have a graph that would look like that, as illustrated in the graph. Now, suppose that each peasant needs 5 bushels of grain to survive. How many peasants would you expect to find working this land? and y. So we would expect to find 400 peasants working this land, and the reason is that at 400 peasants, we have average product or average bushels of grain equal to 5 as well. So basically 400 peasants is the maximum number of people that can work on this land while still being able to survive as well. Note that this is where the average product is equal to the grain needed for survival. So then the number of peasants less than 400 creates some sort of surplus of bushels, and the reason is that for peasants less than 400, we can have average products of either 5.77, 7.07, or 10, and all these values are greater than the 5 that is needed for survival, and therefore we would end up with a surplus. This surplus would force the number of peasants to increase or the population to increase. On the other hand, anything more than 400 creates a shortage of bushels, and this situation causes the population to fall until it reaches the equilibrium population of 400 peasants. Now, assuming we have some improvements in technology, where a peasant invents a new plow which increases productivity by 50%, so that the new production function is now equal to total product, or y is equal to 150 multiplied by x raised to the power half. So for zero number of workers, we'll have total product is equal to 150 multiplied by 0 raised to the power half, which gives us 0. For 100 peasants, we have total product is equal to 150 multiplied by 100 peasants raised to the power half, which gives us 1500 as our total product. For 200 peasants, we have 150 multiplied by 200 raised to the power half, which gives us a total product of 2121. For 300 peasants, we have total product is equal to 150 multiplied by 300 peasants raised to the power half, which gives us 2598. So going on to the end of the table, we get our total product in that manner. Also, you can note from this total product that it's increasing. However, when we graph it, we'll see that it's increasing at a decreasing rate. So as before, we can calculate the average product using the total product values that we have. And we know that average product is defined as total product divided by the labor or the number of peasants. And so for zero number of workers, we have an average product that is not defined, and that's coming from the fact that for zero number of workers and zero total product, we have something divided by 0, and we know that anything divided by 0 is undefined, so that we cannot calculate. However, for 100 peasants, we know that the average product is defined by 1000 divided by 100, which gives us 15 as our average product. For 200 peasants, we have 2121 divided by the 200 number of peasants, giving us 10.61 as our average product. For 300 peasants, we have average product being equal to 2598 divided by 300 number of peasants, which gives us 8.66, and going on in a similar fashion until the end of the table. That would be our average product. So looking at the values that we've calculated for average product, we can clearly see that the values are reducing as the number of peasants increases. So similarly, we can graph the total product or the production function, but it would make a lot of sense if we graph the production function on the initial graph that we had. So the graph that we have on the left shows the production function that we had from the first form of technology that we had. But then with an improvement in technology, we expect the production function to shift upwards. So the shift would be something like that. So that would be our new total product function, or the production function as it were. And the average product would be illustrated in a similar fashion, where if we traced, for example, 300 number of peasants, we had calculated the average product to be 8.66. So tracing 300 peasants from the x-axis, we would draw a ray to the production function, and the slope of that ray would give us the average product of 8.66. In a similar fashion, if we drew another ray tracing 1000 peasants, and from the origin we would have such a ray, that ray would give a slope of 4.74, or that would be the average product. Finally, explain how the Malthusian model predicts this new technology would affect the average product and the number of peasants in the short and long run. This technological improvement will increase both the total product and average product for any number of peasants. In the short run, the new technology would increase the average product and the people will have a surplus of food. However, in the long run, the technology would lead to population growth until there are 900 peasants and the average product is once again 5 bushels. In conclusion, in Malthusian economics, population growth will erode any temporary increase in living standards, ensuring the perpetual misery of the population.